Hello, my name is Frank Silvera, and today I'll be discussing my Lab 8 results. And in this lab, we were tasked with building a 3-bit D flip-flop counter. So we had to follow this schematic, and basically the counter would count up in binary, and this would be seen through the LEDs. We were tasked with setting up the function generator to produce a 1 hertz square wave with a 4.6 volt peak to peak amplitude and a 2.3 volt offset. And this is the truth table that should show the corresponding outputs uh, and how they should be seen in the LED. So for this is 0, 1, 2, 3, 4, 5, 6, and 7, and then we'll cycle all the way back to 0. So for 0, all of the LEDs should be off. For 1, only the Q0 LED should be on. For 2, only the Q1 LED should be on. For 3, the Q0 and Q1 LEDs should be on. For 4, only the Q2 LED should be on. For 5, the Q0 and Q2 LED should be on. For 6, the Q1 and Q2 LEDs should be on, and for 7, all of the LEDs, Q0, Q1, and Q2 should be on. And so we were also tasked with drawing a timing diagram for the clock pulses, and I was able to do this by looking at the schematic. And so the CL, as you can see, there is no bubble here. So when a PGT occurs, is when the Q0, the input that goes into Q0 will actually be registered, and the PGT of the inverse of this of Q0 is what, as you can see over here, the inverse of Q0 is what will determine the output of Q1. And the PGT of the inverse of Q1 is what will determine the the Q2 waveform. And that's what ends up giving you the counter. As you can see, this looks very similar to the truth table. And I even put this on what I observed, that the frequency of each subsequent output wave is halved, and the waves for Q0, Q1, and Q2 also look like the truth table and count upwards in binary. And I will show the video that depicts this counting. As you can see, initially all of the LEDs are off, and I arranged the breadboard in a way so that this is the least significant bit, and this is LED is the most significant bit. So it's going to count upwards. 1, as you can see, this is 1. That is 2. That is 3. That is 4. That is 5. That is 6. And when all of the LEDs is on, that is 7. And then it cycles back to 0 at the end, where all LEDs are off. And that matches exactly with the truth table and also with the timing diagram for each of the clock pulses. And we were asked, why did we connect 5 volts to set and reset to the D-type flip-flops? We did this so the asynchronous inputs would be disabled, meaning the flip-flop will only operate with the CLK inputs. So yeah, these we did that because they are set and reset inputs, and in order for them to not actually have an effect, they have to be connected to the 5 volts. And of course, I explained what I observed. And the frequency is divided, the original frequency is divided by 8 at Q2. Because as you can see, the frequency of the CLK input is divided by 2 for the Q0, which is divided by another 2, which is now a fourth for Q1, which is divided by another 2 for Q2, which is now an eighth. So it's divided by 8.